This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome. A brief pause before the weekend begins. Let's learn some thermo. Before I get to the tapping through slides stage, I just want to talk about where we've come from, where we've gone to. Doesn't feel like we've been going very far for very long, because it's only been 3 weeks up until now. But that 3 weeks also puts you halfway through the intro to thermo. And we've already finished learning how to solve engineering type problems. So the major tools we've been building up so far are based around the first law of thermodynamics, or the conservation of energy. And with that, we've been able to work out, once we've gone through the rigour of determining that states can be determined by properties, and once I've pinned down a state, I can tell you lots of other things about my working fluid, and that the whole point of the exercise is to work out the change that's occurred, the energy required to make a change, the energy released from a change occurring. That's a nice set of tools. It's very useful. It doesn't get us closer to this idea of the best possible efficiency I can get out of a system. So this is what we began talking about with Sadi Carnot's approach to thermodynamics, and the purpose of him undertaking the activity. The conservation of energy ideas don't get him to his goal. They don't get us to our goal. So the thought experiment begins. Cup of coffee. I used to run this thought experiment by pushing a water bottle off, but I want to drink my coffee, so I'm not going to do that. Cup of coffee contains some energy. Let's imagine thought exercise. We seal the room up. It's insulated. So from that point, no mass crossing through the boundaries. Conservation of energy applies. Any energy that's started in the system, we run time to T infinity. The same amount of energy is still in the system. Inside the cup of coffee is something that's transferring heat with the outside world. Eventually we'll reach complete thermodynamic equilibrium. But what's in there? What's in the working fluid there? This is on the assumption that you've drunk a cup of coffee in your life, and do you know that I'm drinking lattes, not just long blacks? What substances are in my coffee? It's not a trick question. It's really not a trick question. If you can't make a cup of coffee, turn to someone next to you who has made a cup of coffee. Hey? Milk's in there. What else is in there? Water. Okay, now we're getting somewhere. And what else? There we go. All right, so now we've made a cup of coffee. And I've stirred it up. And if I leave time to T infinity, infinity is a very long time. Statistically, probability-wise, everything is possible. If I leave things for long enough, everything is possible. How long will I need to wait before the components of my cup of coffee redistribute themselves into water and pure milk and pure bits of coffee? Not a trick question again. Why? It won't.
After a point of time, it will settle down eventually.
Will it become pure milk, pure water, and pure coffee ever again? Okay, this is where we get some fun ideas. I mean, infinity is a very long time. Okay, and so once we imagine very, very long times, we have to imagine all the possibilities. And so one of the answers is, in theory, there could be a moment in time when all the molecules, by random accident, separated out. All our experience tells us this is never ever going to happen. While there is still thermal energy inside this room, and I've sealed off the boundaries, molecules are bumping into each other. While molecules bump into each other, diffusion continues. And for some reason, despite the fact that I've fast-forwarded to T infinity, I can tell you, despite the fact that probability goes on for infinity time, I can tell you this will never, ever go back It sounds like a terrible story, doesn't it? It's heartbreaking. It will never ever be pure water, pure milk ever again. The interesting thing about this, it's not just a cup of coffee story. I could have made it even more human. I could have called my cup of coffee a name, and we could have shared its journey. I don't think you want to share its journey, actually, but the interesting thing about this thought exercise, you can play this game with a lot of other stuff. My bottle of water that I used to do this exercise with, I push it off. Net energy in the room, identical. Fast forward time infinity. A little bit of sound wave has gone out because you would have heard it going plop. The water itself probably were a little bit warmer, then eventually it'll neutralize down. But despite the fact that energy may be conserved, it will never, ever, ever jump back up on the table. Now, you could watch for quite a while. You could watch until you get bored and nervous and people start to giggle around the room, which is some of the other stuff that over the course of this lecture we've done. It won't jump back up. And the point behind that is that, I do have to be careful, I actually don't want to drop this coffee. The point behind that is there are natural directions for processes. We have an idea that there's a way that things will go and a way that things will take effort to go the other way. It's thermodynamics, and one of the things we want to do is rather than just say it is known, we want some numbers and some tools to be able to work that out. And it's obvious that today's lecture is going to be about entropy, if you can read. And so the hint should be in this, that the next tool we're going to develop is about entropy and the second law. Entropy is a bit of a mystery word. It's connected with the idea of chaos. More entropy, more chaos. Less entropy, less chaos. It's also, if you dig deeper into it, statistical thermodynamics. It's connected with the idea of degrees of freedom. And when you're dealing with beyond millions and billions, whatever, 10 to the 23, 10 to the 30 molecules, you have a lot of degrees of freedom. When you freeze them down to 0 Kelvin, minus 273 degrees Celsius, they stop moving, you have no more degrees of freedom. When you let them bounce around, they've got lots of degrees of freedom. And this keeping track of how much bumping and spinning and bouncing off walls goes on actually can be talked about in a magical property. Which is to say, if we can give it a number, I can write down on paper. In the same way as we gave energy a number. So we gave energy a number, kilojoules. I didn't tell you could measure kilojoules. I gave you a whole bunch of tools about how we can determine the change in kilojoules. So our ideal gas stuff, with the internal energy and the enthalpy, these are different measures of types of energy. And I gave you a whole bunch of tools. So the idea of 100 kilojoules, or 1 kilojoule, or a joule, isn't as immediately accessible as the idea of temperature. I can feel the temperature. I don't perceive myself as feeling the energy in the room, although I could pretend that I'm feeling the energy in the room, but I perceive it, I think about it in terms of temperature, which is something I can measure with a stick that's somehow calibrated. The whole exercise of our energy accounting was to give us numbers and rules that let us account for the change in energy. The next step we take is numbers and rules that let us account for which direction processes will go. Which way do they want to go, and which way they're going to require some kind of input to go the other way. So, to spoilers on this idea, which is why I let you see the second law on day one, the basic message is, once I have this counter of entropy, which we will take the time today to define in terms of properties. Once I have this property at a state, and then I have state 2, which means I have another number for the property. The rule is that number can't go down unless I do something. So on its own, generally that number goes up. It's not a given that it has to go up. I could leave it exactly the same. I can have isentropic processes, but I can't have entropy magicking away processes. The only way I can get entropy to go down from state to state, so I can my working fluid can get less entropy if I do something to it. If I refrigerate it, take its heat away, the working fluid will have less entropy. It will be more ordered. If I refrigerate it all the way down to 0 Kelvin, it will have 0 entropy. But my system, my whole system, doesn't win because that heat had to go somewhere. I take the heat out of, let's say I'm refrigerating water, turning it into ice, and then turning it into very, very, very cold ice. That heat had to go somewhere. And if I draw a system boundary around the whole system, what I'll find out is that for my whole system, somewhere entropy went up, more than what I sucked out of the ice cube. So I've created some order in a defined system, but on a big scale, entropy goes up. If you've heard of a concept called the heat death of the universe, this idea is that everything will drift towards thermodynamic equilibrium on a big scale, but also that entropy will be maximized on a big scale, which is to say there will be no more ability to do anything useful. I've got nothing left. The beauty of having low entropy is it's a marker, a measure of how much useful work I can extract from a process. So high entropy things, high disorder, high chaos, are also considered to be low available work, low available useful work. There may be energy. I could have the same, this is important, I could have the same amount of energy. Remember, I've got a counter for energy and I've got a counter for, we're going to develop a counter for entropy. I could have the same amount of energy. One could have low entropy, one could have high entropy. Because processes want to go from low entropy to high entropy, the low entropy energy is more useful to me. I can do more useful things with it. As a hand-waving exercise, as an introduction of ideas, that doesn't give us any maths to play with. It doesn't give us any numbers to play with. So what we're going to do is take the time to map out the maths and the rules that mean I could sit down with a gas turbine idea, I could sit down with a car engine idea and talk about what ways can I make this work better from the concept, from the point of view of extracting the maximum amount of useful energy out of something, which is to say taking it all the way as far deep into the high entropy states. But remember, we have a cycle. If I have a cycle that comes all the way back to the same state, we've got to be careful about how we account for entropy. Because I've just told you, entropy goes up, I've got a system boundary, entropy goes up or stays the same. So it's only under very particular situations can I get back to my starting point. Except that all thermodynamic cycles end up back at their starting point. And so over the course of the next couple of lectures, we will look at the difference between what's happening to my working fluid, what's happening to my system boundary, and what's happening to the heat transfer across my system boundary, which is where that mystery entropy generation occurs. As I lose heat, which is my low quality energy, as I lose heat, if I have heat transfer away from my system, it is taking with it some of the order and leaving behind some disorder. So we will keep extra tabs on heat transfer. And if you remember when we were doing the first law and we're talking about different types of work, our favourite property diagram so far has been the PV diagram, because the integral of it gives me something to do with work, which is to say the area under the graph gives me something to do with work. When we're playing with entropy, the TS diagram, which is what we'll play with, which is temperature versus entropy, the integral of that guy gives me heat transfer. So straight up and down, play with this idea for a bit, straight up and down is constant what? If it was T versus S, T versus S, straight up and down, this is S, so constant entropy. Area under the graph is 0. Heat transfer, therefore, is 0. Awesome. You mastered it. Good job. We don't actually need to do any of the next couple of lectures. That's it. An isentropic process, a process under which no entropy changes, straight up and down on TS diagram. I haven't proven to you that the integral of TdS is heat transfer. We will do that. We'll do that so that these tools are legal for you to use. But just at the me telling you a story level, entropy is connected to our heat transfer in and out of the system. It's connected to our ability to do work. And critically, we will come to the idea that it is absolutely connected to the maximum possible work we can extract from a system, which is the Sadi-Carnot idea. So there will be a definition of the maximum possible efficiency, the Carnot efficiency. There's all these new words and things we will come to play with. The Carnot efficiency is the best possible efficiency you could ever have. And then everything we do to make it more and more real takes me away from that. So that's the preamble. Now, in my notes, the first 3 slides are similar to what I've just explained to you. So for the people who read the notes and want to have different ways for the same idea to be explained, I'll tap them up long enough for you guys to read them. But effectively, that preamble with the coffee and everything tells you what I'm about to show on screen, apart from the tracker slide. So, yeah, I'll get them up on screen. The other things we can think about. The first one is a block, let's say 2 blocks of metal, different types of metal, different masses, different temperatures, and we let them run into infinity time. They're going to equilibrate in temperature. The next one along is, I don't know if you've ever come across a flywheel. A flywheel is a big spinning wheel that doesn't lose energy very fast, and it's powering a motor. That motor's, powering a generator, which is then providing electric current through a resistor inside the chamber. So while it's operating, that resistor is transferring some energy into the chamber. The flywheel is getting slower and slower, and eventually all that energy is transferred into the chamber. And then the third one is our friend, the 2 gases separated by a partition, and we pop the partition, and the gases equilibrate. And so that's the description of each of those things. So if we run into infinite time, the temperature guy will equilibrate in temperature. The middle case, the flywheel will eventually stop with all that electrical energy turned into heat energy inside the chamber. And if it was a vacuum and a gas, that will just distribute. So these are not, you already, it's one of these things, in your mind, you know this. You know that that is what will happen. You know it because you live this stuff, you just have never given it an equation. And so the thought experiment is imagining it going the other way, imagining the 2 heat sources going back to temperature 1 and temperature 2, imagining the heat going into the resistor, powering the generator like a motor and spinning the flywheel, or imagining the gases spontaneously unmixing to leave a vacuum and a gas, which is my coffee example. And all of our instincts scream against this. That can't happen, that can't happen, that can't happen. Okay? So we talk about the more code words, yeah? More thermodynamic code words. We talk about reversible and irreversible. A reversible process loses nothing during the process. And so the amount of energy released during the process, if I put that energy back in, I'd get back to exactly the same state. And an irreversible process has lost something on the way irredeemably. And so it would take more energy than what I released to get back. Friction is the #1 irreversibility. So a frictionless process, pulling something up a pulley or letting it go, the amount of energy I went pulled up, the amount of energy released, same thing. So they balance out. That's called a reversible process, which is to say in state 1 and my returning to the same state released or consumed the same amount of work. And the irreversible process is the one where there was friction in the pulley wheel, for example. And so the amount of work that I had to pull to bring this guy up, some of it was lost to heat. So I was putting more work into the system to get it to pull the weight up than if I let it, than what is released by when I let it go. Because when I let it go, effectively, I'm not really contacting with this thing, I'm just allowing it to free fall. So that's the beginning of the introducing of the code words. Now we have a couple of words, a couple of equations to start to write down. So we say entropy of an isolated system, which is, say, insulated, shielded from the outside world. The universe is one, or a very, very well insulated box. Increases or remains constant, which doesn't sound like a helpful piece of maths. And yet it turns out to be surprisingly helpful. The reason it doesn't sound like a helpful piece of maths is whenever I've got an inequality sign, it doesn't look like I can just easily solve that. A lot of what we do is to solve the problem for the equals sign, look at the reality, and say, was that the same as the equals sign or bigger? And if I did some calculations and it was smaller, I've broken the law. So that's usually how we do it. When there's an inequality sign up there, the law is the law on entropy, so that can't be broken. So if I calculate something that says it was broken, I've done my numbers wrong, or I've missed something. I've missed some work that was put into the system somewhere. You can see terms forming already. I said before that the area under an entropy graph is TdS, and that I was going to somehow link it to heat transfer. And that equation that I've scribbled up there has got my heat transfer and my temperature. It's going to be greater than or equal to 0, which is to say my entropy. So we'll play a bit more with the maths. We would like to show this. And we're going to do it with a relatively simple exercise, which is some melting ice. And we're not even going to put some numbers in. We can just show it by looking at the magnitudes of what we're dealing with. So let's get the words up on screen. And I'll stop talking so you can read. Okay. It feels like, for the first 15 minutes, I'm telling you the same thing in different ways over and over again, because I am. Because notoriously, historically, all the way through the teaching of thermo, for some reason, entropy is the one that people get or they don't get. And so it's also the one that I'm learning, as I teach, I'm learning to say 1,000 different ways, so that one of those ways connects, and we can begin to build up the framework. I mean, the most important stuff about this, even though it feels like a weird concept, is we're going to develop it in terms of properties, which means, in the end, it's just a number I can look up on a table, or I'm going to have a nice equation, and I have to know when to use which. Okay. The property gets the symbol S. My delta S is greater than or equal to 0, and I'm going to define it as my heat transfer out of the system divided by the temperature of the surroundings. That one's important. It's very difficult to evaluate entropy problems, entropy of heat transfer across a system, if you don't know something about the temperature of the surroundings. So there's our problem that we're going to do, which is some melting ice in an isolated system. But I'm going to do it on scribbling rather than... Is it? Yep, that's perfectly visible, isn't it? So let's redraw the system. I'm just going to draw the boundary so I don't draw outside of this guy. Just helps me keep inside the visible box here. So we redraw the system, and we've got an isolated system, which is to say insulated, which means that no heat can transfer. Inside this place, I have a glass of water, and a block of ice. Now, you know the block of ice is floating on the water, but I just couldn't be bothered drawing a floating block of ice, okay? I'm interested in this heat transfer process. In the process of boiling and condensing, I'm at a constant temperature. In the process of melting and solidifying, I'm at a constant temperature. So that's what makes this exercise really, really nice and straightforward. I'm going to call this isolated here. We've just learned a brand new equation. Our brand new equation is my heat transfer across a system boundary divided by the temperature that it occurs at is my entropy. And so the amount of heat transfer I'm going to talk about is Q. Q's worth of heat transfer in kilojoules. And I don't really care how much that was. I'm just transferring water from energy from the ice, energy from the water into the ice, which is going to make the ice melt a bit. So that's the exercise. So my brand new equation, delta S, is equal to the Q over the temperature of the ice. This is delta S ice. my brand new toy of delta S water is equal to the Q. It's the same Q. Yep. It's the same Q. Should have had T's there. T water, T ice. Delta S net is equal to delta S isolated, which is to say it's isolated from the world, from the universe, so whatever goes on is whatever entropy changes happened in the water and the ice. Equals delta S ice plus delta S. I missed the minus. I always miss the minus when I'm writing and talking. Why was the minus there? This is the entropy transfer. This is the change in entropy of the ice. Is the ice getting more or less ordered? Or more or less disordered? More disordered, less ordered. Which is to say, we waved our hands and said entropy is a measure of order, which means I'm talking about entropy up for the ice. The water is getting cooler, so it's getting more order because it's transferring that, it's losing some heat into the ice. So same heat transfer, but I got a minus sign. That guy is getting more ordered. Its entropy has gone down. So I've got this delta S ice. This actually should be net, which is why I do it by hand, to make sure they pick up any typos that I've got in my notes. Minus delta Q water T water. So this equals, I can take the Q out. This. What I'm going to do is say my ice cube was cold ice and it's beginning to melt, and my water is a little bit above the temperature. 1 minus T ice, 1 over T water. This is a small number, this is a big number, which means that this is a big number and this is a small number. Big number minus a small number is positive. So nothing happened in there, no work happened in there. No heat transfer happened outside the system, and yet the system, while we waited, reached a higher level of disorder and generated some entropy. It's our first game. It's our first game with entropy, so we don't need to panic that the very first time I tell you an idea may or may not gel. It's just the first game. It shows you that I can think about the changes of one substance and the changes of entropy in one substance, the changes of entropy in another substance. It shows that I can, in a system, add up all the bits that are changes in entropy. And it shows that now I know that I could put a number on Q. I know that it would be an amount of kilojoules. I know that I can put a number on T. I know that will be some kelvins, which means there is a unit for entropy, which is kilojoules per Kelvin, or on an intensive basis, little s, kilojoules per kilogram Kelvin, which is different to kilojoules and kilojoules per kilogram. So we have a new unit as well as a new property. Let's get this guy back up on screen. I'll do all the things up here. So in the notes, I should have written net and net here. So where do we go from there? Well, it's time for us to start integrating, which is my favourite exercise. It's time for us to start integrating. Integrating on a Friday is not very fair, not very nice, but let's do it anyway. What I'd like to do, this is now the journey of establishing that entropy is a property, not a process. If it were a process, we can't look it up on a table. If it were a property, we can. So imagine we're dealing with water. I could solve a change in entropy problem for my working fluid by knowing the states at the 2 points and looking up the entropy value. If I told you that my process was isentropic and I could determine state 1, I could look up an entropy, and state 2, I could tell you the entropy of state 2 is the same. So I could imagine it's an isentropic process, but now I'm at a new pressure. I'd be on my tables, finding out my entropy, and then saying now the new pressure, what's my new, I've got entropy already. I had entropy and pressure, 2 properties, will pin down the rest of the solution. I could tell you internal energy, enthalpy. I could tell you specific volume because I knew something about the entropy. Well, that's kind of weird. And so it's only okay if we prove that entropy is a property, which is to say it's something that's made up of other properties and not something about process. It doesn't have Q and W in it. So the steps are important because our original definition for entropy changes was a Q divided by T, and that's not a property. So the steps we're going to take now are trying to get rid of the Q, trying to establish that I can talk about entropy in terms of properties. What I did have was that ds had Q and T in it, had dq over T. Oops. There you go. So all we have to do is define the entropy. So we're going to define. I know I flashed some words up really, really quickly. It was all the stuff I've just told you in words on screen, and now we're there. We're going to stick with reversible processes. Reversible processes, as I described them, they're ones where I can keep track of all the energy flows. So if I go from one state to the other, if I release some energy on the way and put that same amount of energy back in, I'll get back to the original place, which is no losses. But state 1 has a different entropy to state 2, but I can get back to state 1 with the same energy transfer. So this is the point of the no losses reversible process. I can get back by putting back in the same energy. For that, we have this idea. With no losses, if I put this guy over here, I get my definition of entropy. So this is a rearranging of that definition of entropy. What I've got is dq equals TdS. We've talked about the units, it's joules per Kelvin, kilojoules per Kelvin. And I can integral. Oh my goodness, I can integral. I can integrate. I can totally integral that. I can integrate from 1 to 2 over S. I don't yet know how T changes with S, so it's not an easy integral to do. But I can begin to write down the integral. I can tell you that if I were to integrate it, then I would get Q. This goes back to that point of, for reversible processes or for processes on the TS diagram, the area under that would be heat transfer. What we need now are a couple of old definitions to plug back in so I can start changing the way T behaves. See if I can actually do something with these with this definition. So what I'd like to do is change the dq part into something that I can express in terms of properties. Is it worth me scribbling these down? Yeah, you know what? Okay, I'm going to. You've convinced me. There was a note that sometimes when the new ideas get flashed up on screen, tapping through them isn't as good as scribbling them down, and I do agree. So that's tapping through them. And instead of that, I am going to jump onto the screen, onto the scribble down document capture, because it's worth doing. I have dq equals t ds. My problem is this guy. My objective is to be able to express that in terms of properties rather than processes. Q is a process. So what I've got is my first law. My first law is energy in minus energy out equals change in energy. What is my first law expressed as the NFEE, the non-flow energy equations? So we've got, you guys have the advantage that there's a guy holding you up, supporting you, because he's got all the answers, which saves me from wasting time trying to ask you. But I need you to be thinking about the answer when I'm sharing it around the room. We spent a lot of time over the last 2 weeks coming up with the idea that my energy in minus energy out equals delta energy. Could be, usually we could simplify that down to heat transfer and work equals change in internal energy. So let's do that. We're going to assume away kinetic energy and potential energy changes and just look at changes in delta U. And so on this guy, if I go here, dq minus dw, we're still in this infinitesimal stage. If I use this, my goal here is to get rid of that. I'm not done yet. I'm not done. If I make a substitution here, I'm not done getting rid of my processes, because work is a process as well. So I need a way to get rid of work. And so what did we spend all of the last couple of days doing? Expressing work in terms of boundary work. So this guy is a P dV term. I'm not going to replace this because U is a property. I don't need to change anything about it. So what I've got now is substituting in here, and I'm going to swap them around so that I can write TdS on one side. T ds equals du plus P dV. This has come from here. If I take this over this side, it becomes a plus, and I've written it as P dV. So it's still saying, remember, in many times where I've derived an idea, I've locked down the problem so that all the rules are obeyed for a little while. This one I've locked down as by saying we are expressing it for a reversible process. It's the tool we use to be able to then prove that entropy can be expressed as a property. And once we've proven that entropy can be expressed as a property, then we're free to use entropy as a number in our calculations from here on in. This is the job of this guy. Which is also to say, if I had pressure and volume and internal energy, I could have ds, provided I knew the temperature. Usually you do know the temperature. Temperature is a property of the system. If I had pressure and temperature, and I wasn't boiling or condensing, if I had pressure and temperature, that's two intensive properties. I could then look up U and V, but I saved myself the time. I'll look up S instead. So, we're at the infinitesimal stage, and we now have an expression for TdS equals du plus P dV, and the beauty of that is it's expressed in properties. So in the same way as we defined enthalpy in U plus PV, we're going to throw in a breakdown of du. So if I rearrange this into this guy, I don't want to scribble this one down. This is just juggling and then differentiating. I take the PV over this side, I do a differentiation, I've got my DH, and my PV gets the gets a PdV and a VdP term, and I already had a PdV here. All right? So now I have two expressions. One in terms of enthalpy and one in terms of internal energy. One in terms of changes in pressure and the other in terms of changes in specific volume. So an enthalpy with a pressure change and an internal energy with a volume change. It is important that we've got two equations, that you know that we've got two versions of writing my entropy equations, because there are situations where you're trying to solve a non-flow problem with internal energy and situations where you're trying to solve a flow problem with enthalpy. And when you're solving a non-flow problem with internal energy, you want to use the internal energy version of the entropy equations. And when you're solving a flow problem with enthalpy, you want the enthalpy version of the entropy equations. This is what I said. Our toolboxes will split and split and split on further and further definitions, and your job is to know when to use which equations. Later on, you can develop finesse in understanding how the equations were developed, but your primary task between now and the mid-sem, which is 3 weeks away, is to get a handle on when to use which equations. So I just heard there's a couple of people, so it's when? It's in the middle of the semester, there's no shock. 3 Fridays away in this room. Just a little advertisement. If I integrate that guy, divide through by temperature and integrate that guy, I get I've got S2 minus S1 because it's from state 1 to state 2 of 1 on temperature du and P on temperature dV. That's if I use the internal energy version. And if I integrate the enthalpy version, I get 1 on temperature dH and V on temperature dP. Now you could imagine 2 things. One, I have, at the moment, for an arbitrary working fluid, I have no guidance as to how temperature changes with du, or how pressure changes with V, or pressure and temperature change with V, and I have no guidance for an arbitrary working fluid, because I've set no rules yet, how temperature changes with enthalpy, or with V and T changes with pressure. So that integral is hard to do. If it were a steam problem, I'd look it up. So, let's not worry about the steam problem. Let's worry about the ideal gas. The ideal gas, I have all sorts of behaviour for how temperature and pressure and volume change. I have the ideal gas law, which means I will be able to integrate these for the ideal gas into analytical equations that I could solve by plugging the numbers in. They're integrals, they're a change in entropy, they imply that there's some kind of reference value, and when we're doing the delta, between state 1 and state 2, we can ignore that reference value. The most common reference value that gets used is absolute 0 entropy, but some textbooks use different reference values, so that's why you don't compare table to table between textbooks. And this is how we imagine entropy. No, this is how entropy does move around. One graph is T versus S, which is the graph I said we would use a lot. The other graph is H versus S, enthalpy versus entropy, which is called the Mollier diagram. In this class, we won't use this one basically at all. But I don't want to say that like a blanket statement of you can ignore how properties move with each other. I would like you to be able to imagine how entropy changes with changes in condition. How does it change with changes in pressure? How does it change with changes in temperature? How does it change in terms of changes with specific volume? So we can already imagine, we have this idea that with temperature my entropy should go up, and we had an idea that when I am boiling or condensing, I stay at a fixed temperature, and yet my argument around melting the ice cube leads us to the understanding that the journey of boiling increases my entropy. So, temperature goes up, entropy goes up. Boiling, temperature no change, entropy up. And then off into a vapour, entropy up with temperature up, a constant pressure process. Go from pressure 1 to pressure 2. Go from pressure 1 to pressure 2 here. I can do that isentropically. That's important to know. My temperature went up when I put my pressure up. I probably know that. It's also possible for me to go up in pressure while dropping temperature, while increasing temperature. This guy, to go this way, went backwards in entropy, so would have required some work. To go this way, went up in entropy, so it's more likely to be an easy thing to do. Okay, we will do the integral. We've got enough time to do the integral. Yes, we do. It's just this page. I show you the goal, which is top right, so that you know we're going to end up with some logs, which means we're going to integrate some 1 on x's. As I said before, if you were at the beginning of the foundation of this science, you don't necessarily know what you were going to integrate or what your target was, so you get the luxury of knowing what the answer is before you begin. But it helps us keep on track and following the equations. Yeah, no, I've got time to scribble this down. We started with T ds equals du plus P dV. This is d little v, specific volume. And we're saying ideal gas. Okay? If I divide through here, then I've got a couple of things I need to know. As soon as I say ideal gas, I can say ideal gas law. I can also bring in my magic friends CV and CP. CV connects for me temperature and internal energy. CP connects for me enthalpy and internal energy. The thing I just said will win or lose you marks in the exam, which is how I get your attention. As soon as I say ideal gas, and I'm in the world, any world, I can use CV delta T and delta U, and CP delta T and delta H. I have an entropy equation in terms of U, and I have an entropy equation in terms of H, which means that if I'm going to do an ideal gas problem and do some substitutions, my entropy equation in terms of U is going to have a substitution with CV and T, because that's what connects me to U. If I'm going to solve an enthalpy problem with an ideal gas, my result is going to have a CP, because that's the tool I use to connect temperature to enthalpy. My hand waving and enthusiasm for this idea is the benefit you get from coming to lecture. This doesn't transmit very well on the lecture capture. So you guys count yourself lucky that you've managed to turn up on the Friday afternoon. This will win or lose you marks. It's one of your toolbox choices. Okay, enough ranting. So this gives us du equals CV dt and PV equals RT. These guys will be my substitutions. They're my substitutions, so I want to bring my temperature over. I've got ds now. It was du over T, and I'm going to substitute in here that my du is actually CV delta T. So if I write down CV delta T on T, this was just du, yeah? I could also write that, I could group these guys. CV is a constant or a variable in terms of temperature? Don't know. Sometimes it is, sometimes it isn't. Depends how big the temperature change is. So bear with me. For the moment, we're going to assume it's a constant. We're going to assume over temperature change is small enough where CV can be assumed to be constant. Partly because I want to get to the end of the integral. Okay, now, this becomes P on T dV. So there was no, I haven't played any games yet with this guy. But my P on T is not something I can integrate with V. I need it in terms of V. And I can do that. And I can do that. CV dt on T plus R dV on V, which is to say this guy, R on V, bring the V over here, bring the T over here, P on T is R on V. Okay. So it's no magic, it's just stuff you're unaccustomed to playing with. Now, R is a constant, and I'm telling you for the moment that we're going to treat CV as a constant, so I have an integral here, an integral here of 1 on x and 1 on x. And the integral of 1 on x is a log, and going from 1 to 2 gives me the log of T2 on T1 or V2 on V1. And so what I get here is S2 minus S1 equals CV log T2 on T1 plus R log V2 on V1. If, this is for ideal gas only, if I started with my T ds equals dH minus V dP, the same games could take me to S2 minus S1 equals CP log T2 on T1 minus R log P2 on P1. All right. It's the same set of maths, the same kind of substitutions. The critical differences here, this guy changes, depending on whether I'm doing the internal energy version or the enthalpy version. And this guy changes as well. That's important. Now, quite often, you will just be, if I'm asking you to solve an ideal gas problem that involves entropy, I will give you these. But you have to know which one to take, and you have to make sure you don't write it down wrong. So you will have already hopefully worked out in your head, I'm dealing with an enthalpy problem, so I need the enthalpy version of entropy equation. There's a couple of other things. What happens if there's no change in temperature? What's the log of 1? 0. Anything in these guys where there's no change in the value that's in the equation drops out. So if I had no change in temperature, this term drops out, but my pressure will still change my entropy. No change in pressure, this guy drops out. No change in temperature and pressure, no change in entropy for an ideal gas. No change in temperature and pressure, what have I just said? 2 independent intensive variables, and there's been no change in them. There's no change in anything. Nothing happened. If temperature and pressure didn't budge, nothing else moved. So of course enthalpy didn't move because it's a property of the state. I might say, I feel like I'm sounding almost angry here. What I'm actually doing is channeling what happens when I mark the exam. And you get a little bit of benefit. This is a couple of years of anger at exams. And there'll be a bit more of it later on. Oops. Yeah, no, that's okay. That's everything I just told you. Except you can't see it. Come on. Okay, so that's everything I just told you. We're now basically at the end. I'll just make a few last quick notes closing on entropy. Many processes we examine in this intro thermo of 6 weeks will have delta S equals 0, and we use that as our baseline. It is worth remembering, this is you looking at the TS diagram, straight up and down on S, that way for increased entropy, because my S is going this way. This is you looking at the graph. Most processes want to go to greater entropy. And a reversible process, this is a tricky one, and I feel like I shouldn't leave your weekend with you. It is possible to have a reversible process with entropy greater than 0. However, an adiabatic reversible process always has delta S equals 0. We will come back to this idea. I don't want you to master this. I want you to have heard of it so that next week when we talk again, it's there. All right, I'll let you finish. And then next week we'll start to use these ideas to solve problems.